This lecture is on the kinetic theory of gases and Graham's law. That these are the principles we're going to learn and talk about the rest of our short week next week. So let's get started. Okay, so let's talk about the kinetic theory of gases. The kinetic theory of gases is a bunch of postulates that defines gases if they act ideally. Now, we talked about ideal behavior in class, and this ideal behavior I kind of made an analogy with students, okay, and I'll continue that Monday, but we're going to talk about kinetic theory of gas. If gases follow these four basic ideas, they will in fact be acting ideal. And if they're acting ideal, what they do is they follow our gas laws perfectly. PV equals nRT. What we have found is that at normal conditions, gases actually deviate from these calculations that we've been doing last week or two by about 5%. And the reasoning is that all gases are actually real gases. Now, a real gas is nothing more than a gas that is not behaving ideally, okay? And there's some reasoning behind that, okay? So an ideal gas is almost a fictional set of circumstances that truthfully can't really exist for all gases. So this gas laws that we've learned, essentially the ideal gas law, is limited by the fact that gases don't follow each other ideally. So let's talk about what that is. First and foremost, I talked about being random. Gases that are ideal. So the kinetic theory of gases is nothing more of a way of defining how gas behaves and how they should behave if in fact we can use these gas laws. So the first thing is that gases are random. They're random particles that are independent of one another, meaning they have no attractive force for each other. Okay. They're random and they're independent. So they don't need or they are not affected by other gases. Okay. And because they're random and they're independent particles, they go in straight line motions. I talked in class how the ideal student will go get a ditto from or the worksheet on the teacher's desk to help the teacher, and if the student was sitting in this spot, it would go in a straight line motion to get the set or stack of papers. It wouldn't waste any time because it wants to go back and watch the teacher. Okay, that's the ideal student. So ideal gas is the same idea. They are not affected by other things. They're not attracted to other gas particles. They're totally independent, and they go from point A to point B in straight line motions. Very important. Okay, the second one. Okay, and this one is not as common, but when these things collide, when particles collide, they collide elastically, I should say. Elastically. Now, colliding elastically means that the particle, okay, when it collides with another particle, okay, transfers its energy, kind of like a cue ball hitting the 8-ball, and the 8-ball taking off, okay, and the cue ball just standing in its place. So you can understand that from my drawing. So if we had a ball that was moving, a cue ball should be the white ball there, hits the, in this case, the blue 8-ball, and the 8-ball would take off, and the cue ball would take its spot. Okay, and we would say that elastic collision has occurred because the cue ball has transferred all of its energy. All the energy in a tank with gas, the collisions are always transferred. Momentum is conserved pretty much. An inelastic collision would be like a bullet, okay, hitting a board and then sticking in that board. Okay, it's an inelastic collision. Okay, but we're going to say they yeah, I misspelled that, elastically. Okay, number 3, and now we're getting to really the meat of the kinetic theories. Okay, the meat of this, yeah, the meat of the more important, or the ones that seem to help students remember this basic set of postulates that define how a gas should act ideally so that the gas laws work perfectly, is 3 and 4. Number 1, or at least the first part of the one that's easy, is that Gases tend to have no volume. Sometimes you'll see insignificant volume or negligible volume, but no volume. Their volume is insignificant, okay, insignificant compared to the space they fly in. So if you think about a gas traveling 300, 400, 500 miles an hour, okay, how small it is and the space that it covers, you would consider its own individual volume to be insignificant to the space it flies in. So that's how they come up with that. And you can see that's already a problem because, well, gases, even though they're small, do take up some space. And that's one of the reasons why, there's no such thing really as an ideal gas. And you're always going to be dealing with some kind of deviation. Number 4, okay, is the one I think is the most important. A real gas really has attractions, and ideal gases, which is basically what these 4 basic postulates mean, real gases, okay, ideal gases really have no attractive forces between themselves. So if I have 2 gases that are acting ideally, they will travel in straight line motions and they would be unaffected by each other's presence. There'd be no attractions. And this is, I would think, the most important one. So an ideal gas ideally has no attractions. And a real gas really has attractions. Got my T there. Now, why is this affect things? Now, I gave you a way to think about this in class. A student, let's go back to our straight line motion because number 4 kind of affects number 1. Because they have no attractions between other gases, they go in straight line motions. Think about our student who is affected by its classmates who are sitting in the class and gets the how can I say, the stack of dittos. He's going to travel in a curved paths around these students before he comes back. What I mean by that is real gases, because they have attractions between other gas molecules, are not independent because they're attracted to the other gas molecules. Now, if you think with me, why does this make these postulates be real or ideal? If you think with me for a second, if I've got gas molecules, I should know that if they're going in straight line motions and if they're independent, then we know that temperature and, let's say, volume would be directly proportionate. All right, increase the temperature, you increase the average motion, the volume has to increase exactly the same amount as the temperature changes. But if these molecules instead have attractive forces, instead of going their individual paths, this one's going to start following this particle. And because it starts bending a little bit, I'm drawing a little more, okay, then its volume is not going to expand as much. If particles are independent, they'll just expand with more temperature. But if these particles have some attractions, they won't expand as much. And they'll be forced to actually coalesce a little bit, somewhat like a liquid, even though they're gases. So you can see how our relationships work if things are independent. Okay. Now, if you think about pressure and volume, we know that this is an inverse relationship, right? Volume is proportionate or equal to 1 over P times that K. We learned about that. And we know as volume increases, okay, the pressure has to decrease. But if you take a piston and you push down on molecules, you expect at higher pressures to have lower volume. But if molecules themselves are taking up space, especially at higher pressures, aren't you going to have more volume than you expect? You expect to have a smaller amount of volume because we're saying that if I press down on this container, that this piston can go all the way to 0. But it won't because these gas molecules take up some extra space that we don't calculate for because we consider them to have no space. So there's extra volume. So this idea that the pressure and volume are going to do exactly what each other does doesn't always occur, especially if the molecules are bigger. You're actually going to have more volume than we would expect because of these differences. And this is some way to think about why um, ideal behavior of a gas drives, okay, PV equals nRT, all of our formulas. So because we have real gases that really do the things that I talked about here, there's going to be some deviations. Okay, sometimes they're small enough to live with, sometimes under different conditions they're too big. In AP chemistry, we talk about the van der Waals equation, okay, that corrects for these. And I'm going to give you a little tour. The van der Waals equation is an equation that tries to uh, compensate for two pieces. Number one, the attractive forces between particles, and two, the higher volume. Okay, and I'll just take a little quick tour before we continue on. Okay, if you look very carefully, I have a real gas, and supposedly volume and temperature are directly proportionate. Obviously, this is going to be 0 Kelvin here, but we would expect a gas to get slower and slower as it gets colder until it stops moving. But we know that some temperatures, a gas is going to condense into a liquid and eventually into a solid. So there you go. Gases eventually do have attractive forces for each other, especially at different conditions. If that wasn't the case, an ideal gas will never condense or never freeze into a solid. But these things do happen. That means gases do have attractions, so it's tough to be a true ideal gas to have no attractive forces. Something else to look at, volumes of real gases at STP. If you look at an ideal gas, 22.4 liters is what we said that universal container for 1 mole. Look at chlorine. Chlorine actually, okay, deviates for that. To have 1 mole of chlorine, it's 22.06. So chlorine, if you notice the differences of the other volumes, chlorine is the least ideal. Look at helium. It matches the ideal gas perfectly. What is happening in helium that's not happening in chlorine? Well, helium's a small particle, has very little attractive forces. Chlorine's a heavy, slow-moving gas, and heavier the gases, the more attractive forces. It's kind of like gravitational attraction. It's called a London force. We'll talk about that. But chlorine, because it's bigger, believe it or not, bigger particles attract each other better. And because it's attracting each other, think about it, these gases are coalescing, and therefore they need less space for the same number. Helium doesn't attract, so its volume is able to fill that container perfectly. So you can see the differences. Gases don't actually fill at 22.4 when they're acting a little bit real. When they're acting ideally, everything works out. Chlorine, we'll go back to that. Now what's happening here? You're seeing something called a term in a van der Waals equation. PV equals nRT, but notice this is minus NB. This minus NB represents a factor to lower the volume, okay, a little bit when you're trying to solve for a real gas. A real gas, okay, so at condition STP, which is a low pressure environment, the volumes calculated from the gas laws are very close to the volumes observed. The MT term is too small to change that. Okay, the observed differences in the molar volumes of the above gases must come from intermolecular attractions. Okay, and I'll talk more about this at another time. All right, the pressure also gets affected. Okay, and let's look at something here. This is called a mean free path. This is an ideal gas traveling. Okay, straight line motions. The gases are totally independent of each other. Okay, now we would say that the mean free path, the distance a gas travels between collisions, is going to be small because they get to the container walls pretty fast. Now, if I have a real gas where there is some attractions, notice they're going to deviate from their straight line motions, kind of like that real student, and therefore they take longer to get to the walls, and the path that it takes to get to the walls is longer, the mean free path. So their pressure is actually lowered. Okay, so a real gas actually has higher volume, okay, than it normally does, and it might confuse some people here, but the reason that chlorine doesn't have a higher volume, even though it's more of a real gas, is because the attractive forces are so much stronger under these set of conditions. We have to change the pressure to see a volume scenario. So that's why the volume's lowered here. Okay, really this is a factor of the attractive forces and the mean free path being longer. I'm sorry, Yeah, longer, okay, because they're being attracted to each other. So this is kind of coalescing and taking less space. Don't get confused about this term right here. All right. Any case, I'll give you another picture of a real gas. It wants to hit this wall, but the other gas molecules are attracting it, slowing it down, making it coalesce into a smaller volume. Okay. The types of intermolecular attractions we're going to learn are H bonding, dipole, London forces. We'll get to that. Okay. We're not going to learn about this van der Waals equation. Okay. Which we notice here's the term. We're going to add the volume to the pressure, and then we're going to subtract some. We're going to add to the pressure because it's lowered, and then we're going to subtract from the volume because it's bigger. Gases do take up some things. So we're not learning about this, but I'm showing you where this all is going. Okay, and again, the term here in this part is all about pressure, and here's here. So I'm going way above this. So let's stop here. Okay, so here's a more of a honors thing to look at. These are real gases. Helium acts as most likely, and hydrogen more like ideal gases because they're so light. Being so light, they're faster, okay, and they tend to attract each other more. Now, this idea of being faster, we're going to get back to it in a second. But let me go forward a little bit here, and let's look at this slide here. Deviations from real gas laws. Real gases have small but insignificant volume. Real gases do exert some attractive forces. These are the two most important postulates we talked about. So if you just remember, real gases really have volume because they do take up some space, and real gases really do have attractive forces. Therefore, their pressure is going to be affected. They coalesce. Now, gases become more ideal under high temperatures and low pressures. This is important. Even though the ideal gas law is flawed, under normal conditions only 5%, but very important, we can make a gas more ideal and use the equation under high temperatures. So if I give it more temperatures, gas particles are more independent, okay? And if you lower the pressure, there's less force pushing together. So higher temperatures and low pressure create particles that are more independent. Gases become more real under low temperatures. They'll start to coalesce and become a liquid. They'll slow down and have the chance to what? Attract each other. And high pressures pushes molecules together. So low temperatures and high pressures will cause more attractions. Therefore, gases become more real. And then there's more deviation. Gases become more ideal, or therefore have less attractions. So these scenario, high temperatures, low pressures, okay, I call this the hand rule. I'll show you in class. That's what to think about. So if I have an ideal gas and I want to make it into a real gas, a gas ideally has no attractive forces, and I want to make it have an attractive force. Guess what? I increase the pressure and lower the temperature. I push them together and I slow them down. They'll attract more and they'll deviate more. I want to take a real gas, which is basically all gases, and I make them go faster. Real gas really has attractions. Ideal gases do not. So I want to lower the attractions by increasing the temperature and lowering the pressure, and they'll expand enough to be more independent. And this is a Regents level understanding of this. Okay. Now this explains in detail the kinetic theory of gases, and the list that I'll have up here is right here. The main tenets of kinetic molecular theory. Gases consist of a large number of molecules that are in continuous random motion. They're random because there's no attractive forces. The combined volume of all the molecules of a gas is small compared to the total volume which the gas is contained. No volume. Attractive repulsive forces are small, and energy transferred is done so elastically. Okay, and these are the four basic things. The two most important are the attractive forces and the volume. Okay, I believe. All right, so we're done with that, and I'm going to make a second lecture, which I have to cover. Sorry, lost the time on Graham's law of diffusion, which will be shorter.